In this video, I'll be going over more optimization problems. This is part 2 of this topic, so if you haven't watched part 1 yet, I would recommend watching that first, just because that video goes over more of the introductory types of problems and just goes through what the main ideas are and strategies for solving these types of problems. Alright, so our first example says a closed cylindrical container is to have a volume of 300 pi inches cubed. The material for the top and bottom of the container will cost $2 per square inch. The material for the side will cost $6 per square inch. Find the dimensions of the container that will minimize the cost. Alright, so let's look at what we have here. We have a cylinder. Okay, and so the volume of this needs to be 300 pi cubic inches. And it says the material for the top and bottom will have one price, and then the material for the side will have another price. Okay, so if you think of this like a soup can, the label, the portion with the label will have one price, and then the top and the bottom will have another price. So what we're trying to do is we're trying to minimize the cost, the material cost for making this cylinder. So if we say the cost is equal to, well, the area of the top and bottom, where we'll be using the $2 per square inch material. Well, the area of the top and bottom is just a circle, and we have two of them. So 2 times pi r squared, that gives us the area of the top and the bottom, and then that's getting multiplied by $2. $2 per square inch. And then the area on the side, well, if you think about it, if you undo, in a sense, or unroll the cylinder, the area of the side is going to be a rectangle. So this area here, when we unroll it, is a rectangle, and this length right here is actually the circumference of the circle at the top and the bottom. So that's going to be 2 pi r, okay, and then this is just h. So the area of that the side portion of the cylinder is 2 pi r times h, and then the material cost for that portion is $6 per square inch. Alright, so simplifying this, we're going to say the cost is going to be 4 pi r squared plus 12 pi r h. Okay, so this is the equation that we want to minimize. Now, the issue with this equation is we have two different variables. We have the radius and the height, r and h. So we're going to need another equation so that we can make a substitution and write this cost equation in terms of just a single variable. So the restricting equation we're going to use is the volume of a cylinder. And the volume of the cylinder is pi r squared times h. So we already know what the volume is. That's 300 equals pi r squared h. So I'm going to solve this equation for h because it's not 300, it's 300 pi. Let me fix that. Okay, 300 pi right there. So we want to solve this for h, and then we're going to substitute whatever we get for h into this cost equation. So I'm going to divide both sides by pi r squared. So we get h is equal to, the pi's can cancel here, so 300 divided by r squared. So that's the substitution I'm going to make right here. So rewriting this, I'm going to have 12 pi r times times 300 divided by r squared. And simplifying that, or multiplying it out, we're going to get 3600 pi divided by r. And I'm going to rewrite that as r to the negative 1. Since we're going to be taking the derivative, it'll be easier if we write this with an exponent. Okay, so now we want to take the derivative. Since we're trying to minimize this, we need to find the critical point. So I end up with 8 pi r minus 3600 pi r to the negative 2, which is the same as divided by r squared. Okay, so what we do is we set this equal to 0 to find any critical points. Again, the critical points tell us where the derivative, which is this equation, where the derivative function is equal to 0. In other words, where the graph of the function has a horizontal tangent line. All right, so solving this equation, 8 pi r is equal to 3600 pi divided by r squared. Multiply both sides by r squared. I get 8 pi r cubed is equal to 3600 pi. The pi, I can divide both sides by pi here. And then we'll divide both sides by 8. So we end up with r cubed is equal to 3600 divided by 8, and then take the cube root of both sides. So I get an r value that is equal to about 7.6631. Okay? So this is the minimum value, or the value that minimizes the cost, the radius that minimizes the cost, I should say. So now what we want to do is we need to find the height. So we're going to use this equation right here. We already have the height isolated, so h is equal to 300 divided by 7.6631 getting squared. So we get an h value of about 5.10873. So those are the dimensions that are going to minimize the cost to build this cylinder. Okay, our next example says that we have a rectangle to be inscribed in an ellipse, and the ellipse has the following equation: x squared divided by 4 plus y squared is equal to 1. What should the dimension of the rectangle be to maximize its area? So let's go ahead and graph what we have here. So this ellipse has a center of 0, 0. And then along the x-axis, we're going out to 2 and negative 2. And then along the y-axis, going out to 1. So the ellipse looks something like that. And this is 2 here, negative 2, negative 1, positive 1. All right, and what we want to do is we want to inscribe a rectangle, and that just means when we draw the rectangle, the vertices are going to be touching the ellipse. Okay, so we want to draw some rectangle so that the rectangle is going to have its biggest possible area while still being inscribed in this ellipse. So since we're maximizing the area of a rectangle, the area of a rectangle is going to be length times width. So that's the equation we want to maximize. And then let's just think about what we have here. I'm going to label this point x comma y. So since this distance here is x, and this distance is also going to be x, the width of the rectangle is going to be 2x. And then similarly, the height is going to be y and then another y. So 2y will be the height, or I guess I'm calling this the length. Doesn't really matter. Okay, so the area equation we have is 4 times x, y. So that's the equation we're ultimately going to be trying to maximize. Now again, this equation has two variables. We need to get this down to one variable. So I'm going to use the given equation to isolate one of these other variables. So we'll say x squared divided by 4 plus y squared is equal to 1. I'm going to solve this for y. And so y is going to be the square root of 1 minus x squared divided by 4. So that's what I'll substitute in right here. All right, so once we make that substitution, we have an equation with just one variable. I want to take the derivative of this equation. Before I do that, I'm going to rewrite this using exponents. Okay, and then to take the derivative of this, I need to use the product rule because I have 4x times 1 minus x squared over 4 raised to the 1/2. So the product rule, I have the derivative of the first function times the second plus the first function times the derivative of the second. So that's going to be I'm going to use the power rule first, 1/2, and then keep the inside function the same, lower the power by 1, and then times, I need to use the chain rule, so I'm going to have to take the derivative of this inside part, which will just be the derivative of that negative x squared over 4. The derivative of 1 is 0, and then negative x squared over 4, well, that's going to be, when we use the chain rule here, we're going to get times negative 2x divided by 4. That's the derivative of this term right here. Okay, so we need to do some simplification. A prime, I'm going to rewrite these rational exponents as radicals. So 4 square root 1 minus x squared over 4 plus, okay, well, this 4x is getting multiplied by negative 2x divided by 4, so those 4's will cancel. So I'm left with negative 2x times x is negative 2x squared times, and again I'm going to rewrite this with a radical, so 2 square root 1 minus x squared over 4 here. And again, we can simplify this 2, and this 2 will cancel. So we get a prime is equal to 4 square root 1 minus x squared over 4 minus x squared times 1 over the square root of 1 minus x squared over 4. All right, so that's our derivative, and we want to find the critical point, and to do that we set this equal to 0. So I need some more space. I think we can do it up here. So we want to say 4 square root 1 minus x squared over 4. So I took this whole thing and set it equal to 0. Now when I set that equal to 0, I'm going to write one term on each side. So I'm going to add the second term to the right-hand side. So x squared times 1 over the square root 1 minus x squared over 4. All right, so what I'm going to do is I'm going to cross multiply here. And I guess it does make sense for me to write this x squared in the numerator. Okay, so I'm going to multiply both sides by square root 1 minus x squared over 4. So times square root 1 minus x squared over 4. Okay, so on the right-hand side, these two terms will cancel. Then on the left-hand side, I have two radicals that are getting multiplied together. those radicals are the exact same thing, so I'm just left with the radicand. So I could rewrite this as 4 times 1 minus x squared over 4, and that is equal to x squared on the right-hand side. So distributing through on the left, I get 4 minus x squared is equal to x squared. So 4 is equal to 2x squared. Divide both sides by 2, I get 2 is equal to x squared, so x is going to be the square root of 2 here. Okay. And I could think of this, I mean, really it's plus or minus the square root of 2, but because 2 has to do with the width of the rectangle, we're not going to have a negative value for the square root, or for that width. So we're just going to use the positive value here. Okay, so we have x is equal to square root of 2, and what we said was the width was equal to 2x. So the width is going to be 2 square root 2 here. And then what we're going to do is I could just substitute in back into one of these first equations to figure out the length. So we'll substitute into this equation, this 2 or x is square root of 2, so I'm going to substitute that in right here. So square root of 2 squared is 2, so I get 2 over 4 plus y squared is equal to 1. That's going to give me y squared is equal to 1/2. Take the square root of both sides, I get y is equal to square root of 1/2, which I can simplify to root 2 over 2. And then the length is 2 times y, so 2 times root 2 over 2 is just square root of 2. So those are the dimensions we have for the width and the length of this rectangle. To find the area, we could just multiply these two together. So we get a is equal to 2 root 2 times root 2, which is going to come out to being 4. So there's all the information that we could be asked for with this question. Alright, and then our third and final example in this video says the regular airfare between Boston and San Francisco is $500. An airline has planes with 300 seats and the planes average 180 passengers per flight. Market research shows that for each $5 decrease in the fare, an average of 3 more passengers will buy a ticket. What fare would maximize the revenue? Okay, so we want to maximize the revenue. So how do we find the revenue? So the revenue is just going to be number of tickets purchased times whatever price they are, so price per ticket. So I'm just going to label each of these things. We'll say the revenue is R. The number of tickets, or the quantity of tickets, I'll call Q, and then the price we'll call P. So we need to figure out what Q is and what P is. So the quantity of tickets that are being purchased, well, we're starting at 180 tickets. That's kind of the baseline. And then what's happening is we're increasing by 3 as we go. So what this is saying is what happens if we have 183 tickets? What happens if we have 186, 189, 192, and so on and so forth? So we're adding in 3 ticket increments, or 3 seat increments. So N is just number of 3 seat increments, we can say. Okay, so the number of tickets that the airline is going to sell is 180 plus 3N. And then the price, well, we're starting at $500, but every time we every time we add 3 seats, that's resulting from a $5 increase, so minus 5N. So when we raise the tickets, or raise the number of seats, I guess it's going the other way. Every time we lower the fare by $5, we're increasing the number of seats. Okay, so we have a value for P, or an equation for P and for Q, so we're just going to substitute these in. So 180 plus 3n times 500 minus 5n. Okay, so we have an equation just in terms of n, so we want to solve this equation. Let's simplify this equation and then we'll take the derivative. I haven't been doing this, but we can rewrite this in function notation r of n. So multiplying all of this out, we're going to get 90,000 plus 1,500n minus 900n minus 15n squared. Rewriting this, 90,000 plus 600n minus 15n squared. And that's what we're trying to maximize. So let's take the derivative of this. I'm going to end up with 600 minus 30n. That's r prime. And again, set that equal to 0. To find the critical point, divide by 30. So n is going to be, 20 here. So what that's saying is we're going to decrease the fare by $5 20 times. So this is saying what fare would maximize the revenue? Well, that's this price equation. So the P is going to be 500 minus 5 times 20. So the price that this airline, that the airline should shoot for is $400. And if they do that, just so happens to be, the number of seats that would come out to is 180 plus 3 times 20. So 180 plus 60 will be 240 seats. So 240 seats is what they would sell in order to maximize their revenue here.